happening intrinsically to the cardiovascular cells that is delaying the potentiation of the signal. Now, we were interested, because of the septal nature of some of these facets, to look at what's happening in the right ventricle. The right ventricle is actually just as important as the left ventricle in normal cardiac function. This was some data from André Livercor's work, some fascinating data, baseline to post-race. In the left side of the heart, you're seeing a drop in left ventricular end diastolic volume, drop in systolic volume. Maybe that's a depletion related to fluid loss, but that could potentially have an impact upon function. Interestingly, in the right ventricle, your end diastolic volume data is going up, as is your end systolic volume data, even more so, which suggests that there's potentially a decrement in right ventricular function. Maybe that occurs before the left ventricle. And this is the data for some of their RV functional data. And you can see the post-race drop and recovery, which is more marked depending upon the intensity of the work. Again, on a case study basis, and this is some of our work from the Western States, this is a 4-chamber view. This is a subtle change, but it's important. This is the RV here, this is pre-race, this is post-race. Hopefully you can see that there is a significant dilatation of the right ventricle post-race, which isn't what you would expect from a depleted individual, from a volume depleted individual. These guys are dilating, much like was proposed by Livercor. What's the consequence of that? Well, here's the pre-race longitudinal strain in the RV. Here's the post-race, a drop again of about 50% in terms of contractile activity. And here's one of the most remarkable images I've seen in a Western States runner. Here is the left ventricle at the end diastolic peak R wave, pre-race, normal circle, post-race, completely flattened septum. So you've got ventricular interaction here, you've got pressure overload in the RV, likely causing some changes in the LV. Okay, summary of that data is that we've got emerging evidence of this concept of cardiac fatigue. I still think it's controversial, and there are some limitations to what we understand. We've got no idea what this has impact in terms of performance. Nobody's ever looked at that. And we really don't know what the true clinical impact is. Most of this change seems to be transitory. It may be that it's actually beneficial for you in terms of the adaptation process. Now, I'll spend just the last 2 minutes or so talking about potential cause of cardiac fatigue, and that's related to this concept of damage. Now, basically, in the cardiovascular world, if you are getting cardiovascular cell damage and you want to make an assessment of some clinical process like acute coronary syndrome, you'll take a blood sample, you'll do an ECG, and in the blood sample you will analyse for a troponin complex. The key is that these troponin complexes with their appropriate antibodies and a lack of transmembrane transporter means that they are highly cardiac specific. You've got an elevation of troponin T, something's happening to your heart. Probably not very good. So this is a cornerstone of diagnosis of AMI. What happens to these biomarkers with marathon running? Well, go back a few years with Rob. We looked at 72 runners in the London Marathon. Not surprisingly, pre-race, no troponin in your bloodstream at all. You wouldn't expect there to be that data there. All of these samples are post-race samples. This is the detection level of the assay. So 78% of our runners had a detectable cardiac troponin, and indeed 11% had a troponin above the most conservative criteria for acute MI. So, run out of battery, I'll keep talking. Basically, this started again a whole sort of slew of studies related to the biomarker release in response to exercise. There's some great data from the Boston races, there's some fantastic data from Germany and a whole host of countries around the globe.
I'll just pick this one out because this is the one with the biggest sample size. This is Fortescue again from the Harvard group at the Boston Marathon. And they saw, again, quite a number with severe elevation. That's how they refer to it. With severe elevation. And they seem to suggest that this may be related to younger runners and with no prior marathon experience, so they're trying to pick out some of the subtleties of individual variability. I think the key message here is basically you've got elevations, again, in about 68% of the runners. This was a sample size of about 450, so this is quite a powerful individual study. Again, we suffer from the same issues in relation to the cardiac data. So we ran a meta-analysis. This is the running-related data here. You can see the heterogeneity. This is a 0% occurrence. This is 100% occurrence. You can see the heterogeneity. The bottom line was, doing the meta-analysis statistics, you expect about a 50% appearance rate in endurance-related activity. That's not a small load. That's not a small number of people. You transfer that to the New York Marathon, that's about 15,000 people crossing the finish line with an elevated cardiac troponin. You walk them into accident and emergency or casualty or whatever you call it, some of those guys will end up in coronary care, whether they have cardiovascular disease problems or not. The issue with this is that, again, all of the data was pre-post exercise. You take one sample before, you take a second sample after exercise, again it could be 5 minutes, 2 hours, 24 hours. The picture was really quite murky. So we ran a really nice study. You talk about people doing things for $100. We managed to get 9 marathon runners to come and run a treadmill marathon. I think we probably bought them a Coca-Cola afterwards or something like that. Pretty tight in the UK. But the interesting thing is, we sampled blood every 30 minutes during the race, and we sampled blood a number of periods of time post-exercise. And these are just the individual traces. First half of the trace is exercise, second half is into recovery. We saw a troponin response in every single run. And in most cases, it was quite interesting. The 8 out of the 9, it was biphasic. There's a release during exercise, and there's a secondary release into the recovery period. That's interesting, because that's biphasic response is actually quite a clinical response as well. But the data are such that the clearance is quite quick, and the actual quantity is quite small. I think if you do something and everybody responds the same way, that to me means that there's probably a physiological process or a physiological cause as opposed to something that's pathologic. Now, the key question, does the troponin release relate to changes in cardiac function? Now, I've alluded to the Neelan data, and there is some association with the Livercor3 paper. If you take the other 60 or 70 papers in this field, there is no correlation between changes in cardiac function and elevation in biomarkers. Why might that be? Well, the very rapid release of the troponin could quite easily come from the unbound cytosolic component of the cell. Only a small fraction, but if it's coming from there, it's not related to breakdown of the contractile apparatus, and therefore won't have a functional consequence. So we think that these two problems are likely different phenomena, unrelated, and possibly in the case of the troponin response, clinically insignificant in this particular format. So, to summarise, in healthy asymptomatic people, marathon running represents an extreme exposure to cardiac work. The physiological stress independent of your training status is going to be substantial. There are often environmental challenges associated with that. We've seen some of David's data, and of course there's often high motivation, people who want to run through the wall or the pain barrier or whatever it is. That, in highly trained and motivated marathon running, can result in evidence LV dysfunction.